We've been talking about dienes and their reactivity, and one of the most important reactions in all of organic chemistry is known as the Diels Alder reaction. It makes use of dienes to create cyclic structures. And so if we have a diene, this diene can react with some other double bond to create a six-membered ring. And this process is known as a 4+2 cycloaddition, so it's very similar to those cycloadditions that we had last semester. But this 4+2 cycloaddition proceeds through an intermediate transition state in which you've got bond forming and bond breaking events at the same time between the diene and the double bond. And so you have essentially a six-membered ring transition state forming. And so the set of arrows that we can draw here involve the formation of a new sigma bond between the diene and the double bond, and another sigma bond forms, and then we form another pi bond here. So there's a net circular flow of electrons to make these six-membered rings. So remember that for cycloadditions, there's this concerted movement of electrons in the transition state, such that these bonds are forming and breaking at the same time. Now, there are a couple of key features of this Diels Alder reaction. The first, as we said, is that this is a concerted cycloaddition. And so it involves 4+2 = 6 pi electrons. And so this is a 6 pi electron transition state. And this 6 pi electron transition state is especially stable. And as we'll learn in a couple of weeks, this special stability is known as aromaticity. All right, so it's got some sort of aromatic character to it. The third feature of the Diels Alder reaction is that it is reversible. Right, so it's reversible in principle, although many times it doesn't happen. The equilibrium is very much in favor of the products here, but in principle it's reversible. This reaction can proceed via both thermal mechanisms, just heating the reaction up, or via photochemical mechanisms. And this would be the irradiation of light onto the system. In this particular Diels Alder reaction that I have shown, we simply just heat it up. Another feature of Diels Alder reactions is that they are stereospecific. So this means that any stereochemical information that you have in the starting materials will be propagated through to the products. And the sixth feature is that it's thermodynamically favored. Okay, so essentially we are exchanging 2 pi bonds for 2 sigma bonds. But despite the fact that this is thermodynamically favored, it's entropically unfavored. You're taking 2 molecules and you are making 1 molecule from those. So this leads to a decrease in entropy. Now we have 2 different reacting partners for the Diels Alder reaction. The first reaction partner is the diene, and so the diene has a structure somewhat like this. The diene is 4 pi electrons, and that diene needs to adopt the S-cis conformation. So it must be able to adopt the S-cis in order for it to react. The other piece that we have is the double bond piece, and we actually don't call it the double bond piece, we call it the dienophile. So the dienophile is 2 pi electrons, And it literally means diene loving. And so it's simply a simple alkene. And so the diene and the dienophile react together using the arrows I have shown to give you a cyclohexene product. And so this is really the first reaction we've come across in which we're making cyclic structures. And so this is a really important reaction in organic chemistry, and is actually one that won the Nobel Prize way back in the early 1900s. So let's do a couple of examples and see if we can draw the mechanism of this reaction. Okay, so if we have this diene here, and we're reacting it with, let's say, this dienophile, and we can heat this reaction up, we can get a flow of electrons, 6 pi electrons, to form a new alkene, cycloalkene. And notice that the two ethoxy groups are on the same side of the alkene in this instance. And so they're also going to be on the same side of the resultant product once we form the cycloalkene. And so we can draw them as dashes now. Could have drawn them as wedges, because this compound will be a meso compound. We can start with a cyclic alkene, such as cyclopentadiene. We can start with a triple bond instead of a double bond. Right? The most important thing here is that you have a pi system. And so we can draw the reaction like this. And so that's going to yield now a bicyclic structure where your formerly 5-membered ring is here, and your triple bond is here. And so we have on that triple bond 2 methyl esters. What was formerly the triple bond is now the double bond. Okay, so we have some other examples that we can choose. So this one here, this diene reacts with this dienophile, and it's going to give us a particular product. And this one is going to be this product here. But we also get the enantiomer. And we'll go and explain why this has the particular regiochemistry and stereochemistry that it has a little bit later on. So these are unsymmetrical systems. We can also have systems that have heteroatoms inside. And so let's say we have this particular diene. This is a diene that's not only cyclic, but it's a furan. And so this furan can then react with, again, an unsymmetrical, let's say, ester. And this can undergo a Diels Alder reaction. This time it's going to give us a bicyclic species which has an oxygen at those bridge heads. All right, it's going to give us this NH, and then it's going to give us this benzoyl ester down at the bottom. It's also going to give us the enantiomer, because we can't create stereochemistry out of nothing. Now, looking at these reactions, you might be able to draw a mechanism for those, and let's do it for the other two. So this one goes like this. But you might be still curious why the products have the observed regioselectivity and stereoselectivity. But what we first want to do is take a look at what's happening at the molecular orbital level. Right? So for the simplest Diels Alder reaction, what's happening with the formation of these bonds? Just the simplest diene, which happens to be in this case 1,3-butadiene. And let's react it with the simplest dienophile, ethylene. And we can draw the molecular orbital description for those two molecules. And so for butadiene, it's going to follow the molecular orbital description that we had previously. And then for the dienophile, it's going to follow just a simple alkene. Okay, so let's see if we can construct these molecular orbitals. So for the diene, it's going to have 4 molecular orbitals, psi1 through psi4. In the lowest energy molecular orbital, you're going to have all bonding. Highest one higher is going to have one node in between carbons C2 and C3. And you notice again that the lobes are bigger in psi1 in the middle, bigger in psi2 on the outsides. Psi3 is going to resemble psi2 in terms of size, but the phasing is going to change in between carbons 1 and 2, and again between carbons 3 and 4. And then psi4 is going to resemble psi1 in terms of size, but this time you're going to have 3 nodes in between C1, C2, C2, C3, and C3, C4. And so if we were to put electrons in these orbitals, right, we would have 2 electrons in the pi1, 2 electrons in the pi2, no electrons in the pi3 star, and no electrons in the pi4 star. And they would again be able to label the HOMO and the LUMO for this. The HOMO is pi2, and the LUMO is pi3 star. Now for the dienophile, this is a little bit different, right? So again, we have still psi1 and psi2, but they're at these energy levels. We still have all bonding in between in between the carbon atoms of psi1, and so we're just going to label it as such. And then in psi2, we have one node, and so it's going to change the phasing. And if we put electrons in these orbitals, we have a pi1 and a pi2 star. We have 2 electrons in pi1, and so that makes this one the HOMO, and this one, of course, the LUMO. And so now what we want to do is to try to see if we can combine these orbitals together to form the resultant cyclohexene. So in order for a reaction to occur, we need orbital overlap that reinforces bonding interactions. And so in other words, the orbitals themselves need to be in phase. Okay? And so we call this control of orbital symmetry, or control by orbital symmetry. And we say that the processes must be symmetry allowed. And so let's take a look at what might happen. So if we're taking the diene, and we're taking it as a nucleophile, it must react with the LUMO of the dienophile. Right, so these two will have to interact with one another. However, if we're taking the diene as an electrophile, it's going to react with the alkene as the nucleophile. That would mean we would have to pair up these 2 orbitals. Right, so HOMO and LUMO are reacting here in both cases, but there's a difference in the way these orbitals are drawn, the number of nodes that they have, the number of the difference in phasing that they have, the difference in size. And so let's see if we can pair up these respective orbitals. And so the first one that we're going to talk about is the reaction of the HOMO of the diene with the LUMO of the dienophile. And that's what's known as a normal electron demand Diels Alder reaction. And in the other case, in which you're reacting the HOMO of the dienophile with the LUMO of the diene, we call that an inverse electron demand Diels Alder reaction. And so let's try to set up the transition state for both of these cases. Diels Alder reaction first. All right, so this is a normal Diels Alder reaction. So we're going to have a diene. I'm going to draw this diene like such, and because we need to basically interact these orbitals, and so we need to approach the dienophile from the bottom face. So there's my dienophile. Now in a normal Diels Alder reaction, again, I'm going to react the HOMO of the diene with the LUMO of the dienophile. So what is the HOMO of the diene? The HOMO of the diene is pi 2. And so I'm going to draw 4 orbitals, and then I'm going to shade it according to the convention that we used for the 4-atom system. And so I'm going to have one node in this system in between carbons 2 and 3. Okay. Next, I'm going to draw the orbitals for the LUMO of the dienophile. Okay, so the LUMO of the dienophile looks like this. We've got shading on one side and shading on the other side. And we could, of course, rotate this 180 degrees clockwise, for example. But the reason I draw it this way is because if you look at the approach of this dienophile, if it's approaching from the bottom face of the diene, you're going to pair up the shaded phase on top of the dienophile with the shaded phase on the bottom of the diene, and then you're going to pair up the unshaded phase on top of the dienophile with the unshaded phase on bottom of the diene. And remember, we also said that in the case of the diene, its HOMO has bigger lobes on the end. And so what happens here is that the end carbons are going to be the ones that make the bonds. And so what you'll see here is that there is an in-phase interaction. This is symmetry allowed. And so there's net bonding here. Right? The orbitals are interacting in phase, and when you have orbitals interacting in phase, they're going to form a bond to one another. Okay, so this is how the transition state is set up and how you generate the cyclohexene product. Now let's take that same approach and do the other case, which is the inverse electron demand Diels Alder reaction. Okay, so in this case we have the HOMO of the dienophile reacting with the LUMO of the diene. Okay, so let's put in the molecular orbitals for the LUMO of the diene first. So the LUMO of the diene first will come from psi 3. And so again, it's going to have those big lobes on the ends. And we're going to have shading that looks like this. Node in between 1 and 2, and node in between 3 and 4. Okay, so in the HOMO of the dienophile, we're going to have net bonding interaction in between. So let's shade it on the bottom, because what will end up happening is you can get, as this dienophile approaches from the bottom, you can get a net bonding interaction between the respective orbitals. So again, this is symmetry allowed. So these are in phase again. And so you can get bonds to form, and they're going to form between the diene and the dienophile on the N carbons. So these two processes are allowed theoretically. They are symmetry allowed. But in the case of the 1,3-butadiene reacting with ethylene to give us cyclohexene, the energy gap between the HOMO and the LUMO in each case is really, really large. Sometimes it's prohibitively large, that it requires really, really high temperatures and high pressures. So how do we overcome this energy difference? Well, we can do two things, really. And so let's actually describe what will happen in the case of a normal Diels Alder reaction, and then we'll describe what will happen in an inverse electron demand Diels Alder reaction. So if we wanted to decrease the energy gap between the HOMO and the LUMO of a normal Diels Alder reaction, we'll probably want to increase the energy of the diene and decrease the energy of the dienophile. In the case of an inverse electron demand Diels Alder reaction, we want to decrease the energy, decrease the energy of the diene's LUMO and increase the energy of the HOMO in the dienophile. So you're always trying to increase the energy of the HOMO and decrease the energy of the LUMO so that they interact with one another. So the question really is, how do we actually do this? How do we increase the energy of the HOMO, and how do we decrease the energy of the LUMO? And the answer is we add electron density or remove electron density. So let's talk about this a little bit more. Normal Diels Alder reaction. We need to add electron density to the diene. This will raise the HOMO. But we also want to remove electron density from the LUMO. Right, so from that dienophile. So how do you do this? You are going to add electron donating groups to the HOMO. What kind of groups are these? These are, let's say, methoxy groups, or let me just say, instead of methoxy, I can add ether groups, so any R group, amine groups, or any carbon-based group, just R. Right? These are it can be grouped into the following category. Things with lone pairs or ability to sigma donate. And what that is going to do is it's going to push electron density into the pi system so that it has even more electron density in it, and that's going to have the effect of raising the HOMO. And so the things with the lone pairs are going to be like the oxygen and the nitrogen, which are going to push electron density into the system through resonance. Or you can push electron density into the system via R groups, alkyl groups like methyl or ethyl, phenyl, that kind of thing, through sigma donation. And so that has the effect of increasing the HOMO. In the case of the LUMO, the way to remove electron density from that dienophile is to add electron withdrawing groups. So these are things that are going to remove electron density from the system. And so these are things like nitro groups, cyanide groups, CF3 groups, any sort of carbonyl group. And so I'll abbreviate this by putting an X there. Okay, and we can say that these are anything electronegative or in conjugation. And this is going to have the effect of pulling electron density out of the pi system. So if you remove electron density from the pi system, that's going to make it more delta plus, and so that's going to lower the LUMO, make it more reactive. And so we can say that the nitro group, the cyanide group, and the carbonyl all remove electron density from the LUMO via resonance. And the CF3 group removes electron density from the system via induction, because those fluorine groups are really highly electronegative. And so one of the examples that we can show is, let's say, the reaction between this one here and this one here. So we have the HOMO of the diene, right, reacting with the LUMO of the dienophile. And in those cases, right, we've got electron donating groups on the HOMO of the diene. So they're lone pairs on oxygen, pushing electron density into the system. You can do this here, or you can do this here via resonance. Or in the case of the LUMO of the dienophile, we have an ester group which resembles that carbonyl, which is removing electron density from the system via this pathway. Electrons on oxygen are very stable as negatively charged. Okay, so if we draw what's going to be the resultant product here, we're going to get a series of arrows like this, and we can draw that transition state that we drew before between the HOMO of the diene, the LUMO of the dienophile, and the product that we're going to get out of this is going to be this one. And of course we get the enantiomer. Okay? Okay, so the lone pairs on the methoxy group are going to increase the HOMO, and the carbonyl decreases the LUMO. And so now the HOMO-LUMO gap is much better, and so you can do this reaction at room temperature or lower temperatures. Let's do the other case. Let's do the inverse electron demand Diels Alder reaction. And so we now have inverse electron demand Diels Alder. So this is going to react the LUMO of the diene with the HOMO of the dienophile. Okay, so here we're going to add electron density to the dienophile. All right, this is going to raise the HOMO. And you're going to do this via, as we said before, electron donating groups. Likewise, you're going to remove electron density from the diene, which is going to lower the LUMO. And this is going to happen via the addition of electron withdrawing groups. And those electron donating groups and electron withdrawing groups are really the same type that we had just previously, but now they're on different types of systems. So let's take a diene now, and let's add in some electron withdrawing groups. And so I've got, let's say this ester, and then let's say we've got a dienophile that has an electron donating group on it, and they're going to react together to give us a new product. That new product is going to be a cyclohexene, and so it has this structure. And of course we have the enantiomer. Okay, we can get electrons to flow like this using the transition state we talked about last time. In the case of the LUMO of the diene, we've got electron withdrawing groups on those that are going to lower the LUMO. In the case of the HOMO of the dienophile, we've got electron donating groups on those that are going to increase the HOMO. So we've got lone pairs on the amine, and we've got a carbonyl system in the LUMO of the dienophile that can pull electron density away from the dienophile, resulting in greater positive charge. Okay, so next time we're going to talk about how to draw these products. We have to take into account both the regioselectivity and the stereoselectivity in order to draw these two products.